time or the resources to get there. Our team developed the GORT device, and this is going to enable users to do just that. Our team is comprised of myself, Fishel, this is Djed, Mohammad, Akhter, Mohammad, and Mounir, and we're under the guidance of our faculty supervisor, Professor Michael. You might be wondering, what is GORT? GORT stands for Geomobile Omnidirectional Robotic Telepresence. So what does it do? The goal of GORT is to provide a user complete roving telepresence. This is going to enable them to be in a situation or a location without physically having to be there. So this is our concept drawing. You can see a user here on his laptop, and he's sending commands to GORT via our 900 megahertz network shown here. And he's using GORT to travel around his office and associate with coworkers, chat at the water cooler, attend meetings, all from the comfort of his home. So how are we going to make this communication between GORT and the person he's talking to good for both ends? So we're going to do this by making communication as personable as possible. We're going to do this by having a microphone and a front camera so that whoever is operating GORT can see and hear the voice of the person that he's speaking with. You can see him here. We'll also have a data radio. This is used for communication with our 900 megahertz network. We have a screen which will show the face of our user. We have a robotic arm for added functionality. Say you want to enter a building via the handicap button. You have the ability to press that and get yourself inside the building. We have a steering camera. This allows a wider angle view. We put a fisheye lens in here. That way you can see door frames and have a zoomed out view of the hallway and see obstacles to get around. We have a back camera so you know what's going on behind you. Speakers so that you can hear the voice of the user. And then we also have omnidirectional wheels. This allows our triangular base to go all directions, 360 degrees, allowing total mobility.
So how do we drive this vehicle? The user will control the vehicle with an Xbox 360 controller. So when when the user presses a button or goes to a certain direction, a command is sent to a base computer through USB, and that command will travel through an Ethernet cloud or network to a base radio. And then the base radio will transmit that command over 900 megahertz radio frequency to the GORT data radio, which will then forward that command to the microcontroller, and then the microcontroller will translate these commands to pulse width modulation to drive each motor independently. The arm movement. The arm movement is controlled in similar fashion as the base is controlled, but we're using a different joystick to control it. And at the end of the chain, the arm command is obtained by a laptop on GORT and then transmitted to the robotic arm via serial port. Now, a lot of people get intimidated by the movement of omnidirectional wheels. So the best way to explain this is simple physics. And as you can see, the white arrow denotes the movement of the whole base. And it's just the sum of each vector force exerted by each wheel. So for example, if you want to move forward, you will have to spin one wheel counterclockwise and the other clockwise with the same speed. And then, for example, if you want to spin, you will have to move all three wheels with the same direction and the same speed. Now, the math behind the movement of the base. We split since this is the two-dimensional movement, we split the plane into 60-degree angles. And then when the user presses the toggle switch, that will create a vector. That vector is calculated in polar coordinates, so we obtain the theta and the radius. And then that vector is split or broken down into three different components. And these three different components will be sent as bytes to the microcontroller. And then the microcontroller will translate these bytes to pulse width modulation signals to drive each wheel.
Controlling the arm was a very hard task, programming-wise. We did it in 2 weeks by doing a motion partition to allow two-dimensional motion partition to allow 3 dimensions of the joystick control to manage 5 degrees of the arm's freedom. So we get the joystick's threshold right there. We can convert it into an angle and send it over the wire. And then once it's on the base radio, it gets converted back into a pulse width modulation via that code, that equation right there.
So we have a lot of parts in GORT, and how do we power them? To power them, we actually created a design of PCB. And this PCB, as you can see, has one input pin that is connected to a 12-volt DC, 200 amp hours marine battery. And we have 5 output pins that are connected to various devices on GORT. And here you can see how our system is wired together. The first thing to bring into attention are the speakers, radio, and the Ethernet switch that is on GORT. They require 12 volts to operate, and we connected them to the pins on the connectors that gives off 12 volts. Next, we have 5 MOSFET switches on our design. Basically, they were used for devices on board that needs to be turned on and off while we're using. For example, we have connected the laptop charger and the monitor to it right now. So for example, you're running low on your battery and you want to save some energy. What you do is you just simply press a button on your Xbox controller and the monitor just shuts off. And we have slots for 3 more devices to be added. We were thinking about an LED pointer to point at device, to point at things, or even a headlamp for motion at night, or even a horn if someone comes in front. You just want to get them to move away from your way. And the next thing, the arm is controlled. The arm operates at 5 volts, and the board gets 12 volts. So we needed to step down this 12 volts to 5 volts, and we have used a switch mode power supply to do so. And the next thing are the wheels. Each of the wheels are connected to its individual motors, and each of these motors requires PWM pulses to operate. So those pins out there, they get pulse width modulations from the microcontroller. Here's the PCB schematic, which was very complex to design because there were a lot of different components that we needed to power. The first thing I need to get your attention to are the 3 H bridges. These actually control the motion of the motors. Next, we have the MOSFET output circuit, and there is the switch mode power supply design. And we also have circuitry out there which tells the user the current that is being drawn at the moment when the base is moving, and also the voltage that is available from the battery. Here's the PCB layout, and you can see there are a lot of thick red traces to handle currents up to 25 to 30 amps. That's how much current GORT draws when it's at full speed. And after the PCB was manufactured, we actually have to test it, definitely. First thing we did was test each individual pins to find out whether the right amount of voltage was given to it. And the next thing we did was verify the MOSFET switches and tested whether it actually turned on and off the devices we want to appropriately. And we ensured that each of the H bridges gave a constant PWM to the motors so that there was no jitter, or we ensured that each of the wheels get the same amount of current. Finally, we confirmed that switch mode power supply actually brings down the 12 volts to 5 volts. And we also found out a problem with our design, and that was found at the last stage, that the IC chips that we were using actually heated up a lot. And we did not design for a heat sink, so that created a lot of problems while operating the H bridges.
So we were testing the GORT base to see if we can control it remotely, how much deviation from the norm after we put all the stuff together. It's giving a lot more weight to it. And it was, to our expectations, almost no deviation at all, around 2 or 3 degrees over that long distance. The battery was said to be 200 amp hours. It should have calculated out to be, if we managed it on full power, if we were moving it continuously for 2 hours straight, it would lost the power to 130 minutes approximately. When calculated and done through testing, it was about 117 minutes. Okay, now for the communication, we had several generations of our software. The first, at the end of last semester, we created a software that was running on TCP. The lag and the delay was significant. In terms of milliseconds, it was about 400 milliseconds latency, and the bandwidth was also being consumed at a really high rate. It was streaming an MP4 video stream. Then we decided to convert that into a UDP early this semester. So in February, we changed it to a UDP system sending images, JPEG images. And now the problem with the TCP was that the delay was increasing over time because it was buffering. So now when we were sending images, that didn't happen. But still, there was a significant delay that you couldn't control it. You can move it before seeing the video feedback. So in March, we used H323 protocol, but the H323 only had audio, it didn't have video, so now our audio was preceding our video. Also, our metrics were a little bit better with bandwidth. So in April, to fix this, we used a standard development kit that that ensures balance over TCP, UDP, uses all the latest video conferencing metrics like SIP, like RTP, and OpenH323 protocols. So this is actually turns out better than Skype with 3 video feeds. This is a look of we can move the windows around, but this is a good look at how the user will be able to see the system. And now for GORT in action.
Alright, and I'll be talking about our contributions. So the total amount of hours that have been put in this project add up to 1,050 hours. The total amount of money that was spent in this project add up to 2,500 hours. And I'll be talking about the special task of each team member. Mounir Fishel is our project and financial manager, and she helped on the circuitry and building the body of GORT. Muneeb Akhter is our software development, and he worked on the audio and the video communication and the programming of the ARM. Mohammad worked on the circuitry and the PCB design. Djed is our technical manager, and he worked on the base movement. And me, myself, as Mounir Amer, I worked on the circuitry, hardware, and the wiring. Lessons we learned. Nothing goes according to plan, so always try to plan ahead of time and try to test as much as you can, because you definitely get better results. And if you're on schedule, you're behind the schedule. We definitely learned that. And you try to work smart, not hard. I mean, don't put stay till 5 in the morning like we did this semester. Other than that, buy a lot of extra parts and components. You always need it. In our occasion, we always have the MOS transistors are always burning, so we had a lot of NMOSs. And definitely, you need to have good communication between all the team members, and that's a must for being successful. And acknowledgement, we would like to thank Professor Young for all his guiding and advising that he gave us this semester and last semester. We would like to thank the art department, because they always let us in the metal shop, and we could use their tools. We would like to thank friends and family who always supported us, and the GORT Wireless Network team. Any questions?